Hello everyone, and this is gonna be the last lesson before we jump into the exam. Okay, so in this session we call this session conditional expectations. So the motivation is that suppose we wish to predict one random variable y. Okay, so we have a random variable y. If we want to predict it, let's say minimize MSE, so we can predict it using the mean. Okay, however, if we have another clue, that is the information about x, okay, and we have the information about x. So if we have the information about x, we can help it to guess the y. Okay, let's say from the linear regression, for example. Okay, let's say x is the age, okay, y is the income. So we have the age, okay. That is, we have to construct the age as a function of the age. Let's say f of h, such that f of h is going to use to predict what? Predict the income. Let's say the income hat. Okay, the income hat. This is the goal of the linear regression. All right, but fundamentally, linear regression is the concept of the conditional expectation. We condition on seeing the let's say the explanatory variable. Let's say we wanted to use age to predict the income. So the income, the predicted income must be the function of age. Okay. So let's see. The definition. So the conditional expectation. In this slide, we have to be careful in reading the notation. So see, let's say roughly, you can say that, oh, expectation E, Y, H is going to be a function of two random variables. The answer is no. Okay, the answer is no. Why? Because if we see this carefully, integrate of this one is a function of y and x. Yes, a function of y and x. Function of y and x. But we integrate with respect to y. That is, we flatten out this one. So what variable is left? It is the x. So the e of yx is the function of what? It's the function of x. It's not the function of y. And it's not a function of both variables. Okay, it's a function of x. Because we integrate, we get rid of y here. Okay, it is a little bit strange because normally we can say that, okay, it is y is at the front, it should be the random variables, right? Or both of them. But in this case, it's a function of x. That is, if we plug in x, we get what? We get the function of y. That is e of yx. Because the input is x, input is not y. Okay, so e of y is going to be, let's say, h of x. Okay, let's here h of x. So it's going to be function of x. Next, the law of the probability. Let's say the expectation of the expectation is the expectation of y. Okay, so how do we going to prove this? Are there any proof in the next slide? No, right? Okay. So let me prove this because it is essential to go to the proof of this in detail. Okay. So what is e of yx? It's going to be function of h of x. Because we have input that is the x. Right? Can be y g of y given x and dy. Okay. But how about if we put another expectation here? What happens? It's going to be the constant now. right hand side, we should expect the constant e of y, right? So for this one, we integrate another integration of y, d of y x, and we have what? We have dy. It's gonna be f x dx. If we combine all of this, what happens? Y gyx fx dy dx is a joint. It is a joint, right? Let's say fxy dy dx. Okay. So this one is what? The expectation of y. So if we use two expectation, what should we expect to get is the constant. This one is not the function, it's not the random variable, it's a constant. Okay. This one is the function of x. Okay, this one is the function of x. Okay. So let's see. Suppose that a point x is chosen in the quadrant of uniform distribution on the 0 and 1. Let's say. So let me draw the picture to illustrate this problem. Okay. So x is between 0 and 1. Let's say it is chosen. Okay, for example, 0.3. Okay, 0.3 is the x. After 3 is chosen, okay, y is chosen between x and 1. So what is the expression of y? So it goes back to the chapter 2. Okay, chapter 2 we talk about the concept of the condition. Okay, the conditional probability. We talk about the base rule of the thing here. That is, if we know x, y is easy. Okay, so we can use the identity here that if we know x, we know y, that's easy. So we can take the double expectation here. Okay, so this one is easy to find, right? Because it is between x and 1. So it must be 1/2 of x plus 1. Okay, so we have to take the expectation of this one. It's gonna be 1/2 e of x plus 1 is gonna be 3/4. So let x and y be random variable, and let's c be the r of xy for some function r. The conditional distribution of c given x is the same as the conditional distribution of r xy given x. That is, any random variable doesn't matter, because all in all, even though it's the y or it's the x or it's everything, here it is a function of x. Here's a function of x. It doesn't matter what the y is, because if you look at the last book, we didn't mention about y. Okay, we can replace y by r xy, because here is a function of x. But if we combine with the other expression, it's gonna be the constant. That is, we have to take the expression of r xy, and the right hand side is the constant. Okay. So we talk about the conditional expression. So now, when we talk about the conditional variance, that is, we have the variance of y given x. Okay. Similar, very similar to the conditional expectation here. Okay. And it is a function of x. Okay. And we have this identity. This identity is not difficult to prove. Okay. But we are not going to prove here because it's a little bit messy, but we can prove. Okay. So the way to get sense about this is that if we wanted to find the variance of all the group, right? Let's say that, okay, it's a y is one group, right? is another group, and what is another group. Let's say it's X1, X2, and X3. Okay, I think we should use different color. Okay, X3, and let's say X2, and let's say X1. So the variance is that we find the variance within the group first. Okay, the variance within X1, the variance within X2, and the variance within X3. That is this term. Okay, variance within group. But within group is not enough. Okay, because even though within group it is clustered around together, but each group is far from each other. So we have to find the variance between group two. Variance between groups. Okay, is one way, let's say, to make sense about this one. It is used, let's say, in clustering, I guess. Yeah, because we can find the model, okay? We can find the model with this. Okay. So by using the conditional expectation, we can say that similar manner. That is, we have the x. We want to find the x that minimize the MSE. So minimize MSE, it is rather than the mean, we have the conditional mean. So how to prove this? Okay. So we have to define d star x. D star x is an arbitrary predictor. Okay, the arbitrary predictor. We can define this one into this together. And then we find C here. Okay, H is equal to C and C star is equal to this. This is about the something about the logistic. We just define some variables here so that we can write the proof more easily. Okay. The next slide is about the real proof. That is, we have to compute this one. Okay, it is reduced to this one. That is indicate Hx is less than or equal to H star x. But we have F1x in common. That is, we have to show only this one. Hx is less than or equal to H star x. Okay. When we condition on x equal to x, it is the constant now. It is the constant now. So we can prove this one. That is, take x as the constant. For every x, take x as a constant. So we can find that it is minimizing MSE that we found earlier. We condition on the x, and from that distribution, we can say that the dx e of y given what? Given small x, it is the minimizer. But if we need minimizer for all the x, therefore, d of the big x is gonna be what? It's gonna be e of big y given big x. It is h of x. Not h of x in this sense, okay? So another example. Let X be the number of patients out of the first 40 in a clinical trial to have success as their outcome. Let P be the probability that an individual patient is a success with a uniform distribution over 7 months before the trial begins. The outcomes of patients are conditionally independent given P is equal to P. So how do we find this one? Okay. The thing that we want to find this one is that we wanted to minimize MSE. Okay, we wanted to minimize MSE. In predicting the P before the observing X. If we wanted to predict P before observing X, so we get the what? The mean, right? The mean of the uniform, it is 1 plus 0 over 2. That is 1/2. MSE is 12. So we want to find MSE for another purpose, but let's keep track of MSE and P. However, let's say we perform 40 trials and we get the outcome. So for this one, we could get a little bit clearer picture about the P should be, right? So we wanted to find the P as a function of X. X is a predictor. It's a predictor. And what about the P as a P hat? That is the prediction from the using X as a predictor. So first, find the conditional of P given X. We get this one is. I think you all can do this, okay? Because we have covered this in chapter 3. But you can do this as a homework, okay? But it's not difficult at all. You can find this in chapter 3, okay? If we would like to minimize MSE, the thing that we should do is that, okay, so the P is a variable, right? And this one is a T of P given X. After the integration, we have X plus 1 over 42. X plus 1 over 42. So it is very similar to the frequentist one, right? So for the regression here, one is called the Bayesian estimate because we minimize the, let's say, the MSE using the expectation. So it is very similar to X over 42, right? It is a frequentist estimation. So the Bayesian estimation has another advantage. That is, if, let's say, for example, we have, let's say, so we can integrate this into X plus 1 over 40 plus 2, right? It is the form, right? X plus 1 over N plus 2. So as we get more and more and more and more data, we're going to get close to this. But if we get no data at all, it becomes the initial guess that is 1/2. But if we use a frequentist, if we do not have any data at all, we get 0, which doesn't make sense. Okay? So we need to calculate the MSE. The MSE after solving X equal to A is this one, okay? But this one is not enough because any X, we get different variance. What we are going to do is that we take the expectation of this one, okay? After we take the expectation of the variance, we get this one. So this one is a little bit smaller than 1 over 12. That is by having X as a predictor, we can actually reduce the error, okay? Reduce the MSE from our prediction, which is, it doesn't make sense because if we have the predictor, the worst that we can do is that we do not get any information at all, okay? But maybe there is the worst thing that's called overfitting, but let's say we didn't talk about the data science here, okay? So we do not talk about that issue, but generally, as we have more and more data, so we could get less error, okay? In general, that is this one, okay? So this one is the conditional. The conditional varies based on the X. That is, if P is very close to 0, we should use the marginal, right? We should use the marginal. But if no. Here we just, because this one is density, right? Okay. So the marginal, whatever X is, the P stay the same, but The conditional, we have the variation. It depends on the predictor that we get. Okay? So we have finished the chapter 4 already, right? And in the next lesson, we're going to see the big picture. Okay, I'm going to give you the summary of what we have studied over the past few lectures. And in the next 2 lessons, we are going to go through some problems. Okay, some problems to see this in the exam question. Okay, so see ya.